let me summarize the covalent bond information about the covalent bond. This is the first is that valence electron in atoms are sharing and partially electron sharing, or we call shift. So as you can see, like sulfur and oxygen, these two atoms bound together, and then the electrons are sharing to each other. Okay, and then you need to know covalent bond is share and shift for the electrons structure. The second is that the Lewis structure. You know, if you have different atoms together, you need to know how to draw the structures. So we have rules to draw a structure, for example, like this. Important thing is that the bond between chlorine and sulfur is the bond which with two electrons, right? And the point 3 is that you need to know the shear hybridization. You know, for example, methane has one carbon, and it's sp structure. So you have the bond with 4 electrons. You have the bond 4 electrons of the hydrogen. So this involves hybridization. And point 4 is the energy of the heteronuclear bonds, like XY. As you can see, this is explanation of the energy for the bonding of the X atom and Y atom. And point 5 is that we need to know the ionic characters of the covalent bond. The equation, as you can see, expressed as showing here. Okay, this is called ionic character. You need to understand. And then finally, we talk about dipole, polar bond, and the polar moleculars. And you need to very clear with these 3 terms: dipole, polar bond, and the polar moleculars. Okay, and this will be the question of our Kahoot today. So remember, you need to distinguish. You need to find out, is this molecule has dipole polar bond or not, and is this molecule is a polar molecular or non-polar molecular. Okay, this is important. And in the end of the lecture last Friday, we talk about if we have molecular 2 atoms together, we need to know how their molecular orbitals looks like. And then we need to know the energy of this molecule. So that means it is involve atomic orbital Schrödinger equation, right? Schrödinger equation, and we know Schrödinger equation is linear. So we can combine the atomic orbitals to become a molecular orbital. This theory is called LCAOMO. Okay, LCAOMO stands for linear combination of atomic orbitals into molecular orbital. Okay, and for the energy, so now we know how to draw the orbitals and how to realize the orbitals. And then for the energy, we need to follow 2 rules. The first rule is conservation of the energy states. And second rule is the alpha principle. Okay, so now let's go into this topic we want to talk about today. So first of all, let's think of s orbital and s orbital mixing. I mean, I have lithium and lithium, or I have hydrogen or hydrogen. So this is called homonucleus diatomic molecules. So s orbital. You know, this in the periodical table, this is s orbital, and this is p1, p2, p3, p4, p5, p6, right? Okay, so now we are talking about this. We want to know the orbitals, the structure of the orbital, and also we want to know the energy of these molecules. Okay, So let's think of the hydrogen first. This is hydrogen. Let's use the most easy case or most easy example to understand the orbital and the energy. So we have two hydrogen atoms. They are very far away to each other. So there's no interaction between each other. And we understand there's one electron for in the hydrogen on the right hand side, and we have left hand side, and we have one electron in the hydrogen atom in the right hand side, left hand side. And now we put it, so if we have a large separation, that means there's no interaction, right? But once we close these two hydrogen to each other, and they have attraction and repulsion force, as you know, and this represents the probability of the electron in the atom, right? So the atomic orbitals start to interact, and if we start to interact, that means we need to follow LACOMO, right? LCAOMO. So they start to smear together. So to form a shared molecular orbitals. So it looks like this. So we have bonding from here to here. We have electron pair bonds. This is covalent bond. We already learned this in the last week, right? Okay, this is the shape, or this is the orbitals of the hydrogen. How about the energy diagram of the hydrogen? So again, we start to draw the energy level diagram. Energy level diagram tells us that if I have one electron here, that means it's minus 13.6 electron volt, right? According to Bohr atomic model. So energy from low to high and reach to zero, that means the electron will be the free electron, okay? And we have another we have another hydrogen atom. Again, they are very far away, so there is no interaction. So you can draw the diagram, energy diagram like this. So once they get together, so two electrons are far apart, they can be like this. Energy level diagram can be like this. So this is 1s atomic orbital. AO stands for atomic orbital. 1s orbital. And then we have one electrons. So as you know, each electron has its quantum number, right? So this quantum number will be 1, 0, 0, and 1.5, for example. And also another electron will be another atom will be has one electrons. Again, this electron has its own quantum number. Okay, when there are two atoms are far apart, it looks like this. So once we make these two atoms get together, we will form the hydrogen molecule. When we form the hydrogen molecule, we have to follow two rules, right? The first rule is the conservation of energy state. That means you have one energy state, you have one energy state, and you have one energy state. When you put these two to become a molecule, you have to become two energy states. This is conservation of energy state. For example, if you have three energy state, you have three energy state in one molecule, one atom. You have another three energy state in another molecule, another atom. If you put these two together, you will have what? You have 6 energy states. Okay, so and then the second rule is that once you have 2 energy states, and how are you going to put the electrons into this molecular energy state, 2 energy states? You have to follow alpha principle. Okay, so conservation of energy state and then Pauli and alpha principle. In this case, we follow Pauli exclusion principle. Okay, let's show 2 energy state here. And these 2 energy state, the energy has to be balanced with this one, right? Okay, so one will be on the top, one will be in the bottom. Okay. And then now we need to put these 2 electrons into this molecule. So the first one, you had to put in, the first one is you had to put in the lowest energy state. This first one. How about the second one? The second one, will you put the energy electron here or here? Here, right? Because you follow Pauli exclusion principle. And this if this spin up, this need to be what? Spin down, which is different from this one. Okay. So this is how energy level diagram of hydrogen looks like. Okay, and then in this case, this energy state we call bonding molecular orbital. Bonding molecular orbital. And this one we call anti-bonding molecular orbital. Or somebody read anti-bonding, but British accent, anti-bonding molecular orbital. Okay, no problem. Okay, so this is the energy level diagram of the hydrogen. By forming hydrogen, the energy of the system is decreased. So this hydrogen atom, the energy is here, but when you form a hydrogen molecule, energy level is decreased. So which one is more stable? Hydrogen atom or hydrogen molecule? Hydrogen molecule, right? Because energy level is lower. That means the system energy is decreased. That means this molecule is more stable than this one. Okay, so when you do the simple calculation, and you will realize when you do this, and then you got a minus 435 kilojoule per mole. That means this molecule release energy. It make the system more stable. Right. So you might think, well, Professor, here when we just talk about the orbitals, this is the molecular orbital, and then, however, there are two bonding molecular orbital, right? This is called anti-bonding molecular orbital. So there are two orbitals. So how it looks like? So when we have two orbitals get together, as you know, you have constructive interference. This is bonding molecular orbital. So for 1s and 1s, this constructive interference, and how it looks like is this is constructive interference. So we have bonding molecular orbital. However, we have another one which is called destructive interference. You know, if we regard hydrogen atom as a gas, and as a wave, and then you have destructive interference. The destructive interference, the orbital looks like this. So this part, they overlap together. The part which two orbitals overlap together, and which has a destructive interference. So you will remove all of this electron probability in this region. So the molecular orbital looks like this. So this is what we call anti-bonding molecular orbital. Right. So hydrogen molecular orbitals looks like this. So this is called anti-bonding molecular orbital. This is anti-bonding molecular orbital. And there's a plus sign and negative sign. It doesn't mean anything because the textbook just want to tell you that it just want to distinguish the orbital on the right hand side and the orbital on the left hand side. Okay, of course, this is also according to the Schrödinger equation, wave function. So when we say hydrogen molecule is more stable than hydrogen atom, then how about the hydrogen molecular cation? That means what? You have one loose here, right? Is this stable? Hydrogen molecular cation, is this more stable than the hydrogen atom? Yes or no? Yes, right? Because the energy state is lower. even though you lose one electron, this energy level is lower than this one. So it's more stable than hydrogen atom. Okay, so let's take a look of the 2s1, which is lithium. So lithium is the same case. It just different is from principal quantum number from N1 to principal number from N2. That's it. So lithium has 3 electrons. So you have S1s2 and 2s1, right? 1s2 and 2s1. So when you put these 2 lithium atom together, anyway, according to the conservation of energy state, you will have what? You will have 4 energy states, right? You will have 4 energy states. And again, one is bonding molecular orbital, one is anti-bonding molecular orbital for the 1s orbital and for the 2s orbital. Again, and you start to fill the electron into these molecular orbitals diagram. So you have 1, 2, 3, 4, right? Okay, and then now you fill another one here, 1 and 2. So you have 6 electrons. However, as you know, when we talk about the electrons, we always talk about the valence shell electrons only. Only we talk about this part because this is the place where you have more chemical reaction. These 2 electrons take place, the chemical reactions. Okay, so we only discuss the valence shell electron. In the future, we don't talk about this, the electrons in the inner shell. And again, once we want to know is this more stable compared to is lithium molecule is more stable than lithium atom, we do the calculation, or we see the energy level diagram, and we realize is this stable or not. So as you can see, lithium molecule is more stable than lithium atom, right? So by combining 2 lithiums, the energy of the combined system is lower than the energies of the atomic systems. So lithium molecule is stable compared to lithium. So you might wonder, Professor, why I never see lithium molecule. I only see lithium is a solid, right? So you have 1 Avogadro lithium cube, right? You have it's a solid. So as you can realize, here we just talk about 2 lithium atom get together become molecular is more stable than 1 electron, 1 atom. And after that, we are going to talk about metallic bonds, this is more stable than lithium molecule. So lithium exists as a solid containing many lithium atoms bonded together at room temperatures and pressure. So this lithium solid or many lithium solid is more stable than lithium molecule, and is more stable than lithium atom. We will talk about metallic bonds in the about this in the future. So now, when we don't want to give you more example about sodium and potassium because rubidium or cesium and francium. Okay, it's the same concept. So this is 1s to 1s molecular orbital get together. Okay, so you just make the difference is ns. If n equal to 1, that will be hydrogen. N equal to 2, that will be lithium. N equal to 3, that will be sodium, etc., etc. Okay, and of course you understand if you this energy divided by summation of this energy is stable, so it looks stable, so it's favored. Right. So next topic we are going to talk about bond order. Ladies and gentlemen, this is important. Please remember this. Bond order. We use BO for short. Bond order is that what? Bond order is the number of the bonding electrons minus the number of the anti-bonding electrons. and you have to make it blanket together and make it and divide it to 2. Okay, let's make an example of lithium molecule. Lithium molecule is how are we going to determine the bond order? Bond order is that I have the number of bonding electrons. Number of bonding electrons. How many bonding electrons? 1, 2, 3, 4. Right? 1, 2, 3, 4. So I have 4 bonding electrons. And how many anti-bonding electrons in the bonding molecular anti-bonding molecular orbital? 1, 2. Right? 1, 2. So you have 2. So 4 minus 2 and divided by 2, and that will be 1. So this is called bond order. Bond order. However, as I just told you in the previous slide, normally we don't talk about the electrons in the inner shell. We only talk about the electrons in the valence shell. So in the valence shell, we can simplify this bond order. Simplify this one. How are we going to simplify this bond order? Because as you know, this 4, you would remove these two together, so it doesn't make it different. So what you need to do is calculate the electrons in the valence shell. So let's refresh this equation. Is bond order equal to 2? I have 2 electrons in the bonding molecular orbital. I have 0 in the anti-bonding molecular orbital. So as you can see, these 2 equations tell you the same answer, which is the answer is 1. If bond order is 1, we call this single bond. Single bond. So this bonding has, for example, lithium and lithium get together, they only have 1 bond only. Now you might say, wow, Professor, how about the bond order is 0? That means there's no bond. How about 2? If you got the answer is 2, that means what? Double bond. 3, triple bond. How about 1.5? It's 1.5 bonds. An example is benzene. Benzene is 1.5 bond. Okay, so you can do this simple calculation to tell yourself, to know that this molecule, how many bonds in this molecule. And what happens if I have 2 bond, a double bond or a single bond? As you know, the larger bond order indicates a great bond strength. It means what? If you have a double bond, that means this double bond is difficult to break it. Require higher energy to break this double bond. Right? So let's think of the helium. That's S2S2. This is one of the example. Okay, here S2S2, that means what? You have 4 electrons filled in the anti-bonding molecular orbital and anti-bonding molecular orbital. At this time, you might think, wow, how about the energy? Is helium molecule stable? As a matter of fact, you have to think of the energy. You have this energy in the molecular orbital, and you have energy in the bonding molecular orbital. You have to put this energy together and to see whether this energy is lower than this energy or higher than this energy. That's what we do, right? Okay. So when we do the calculation, we find out that this is not favored. That means these 2 energy get together. This is higher than this. So energy delta E is less than 0, so it's not stable. So you might say, wow, Professor, why this is not well disputed? Well, when you just measure it, it's not well disputed. It's not half-half. However, if you do the bond order, this is not stable. It's 0. Bond order is 0, right? Because 2, 2. 2 minus 2 is 0. So bond order is 0. So it's not stable. How about if you lose 1 electron? If you have helium molecular cation, is this stable? Yes, compared to this, right? This energy will be lower, and then so helium, there's only 1 electrons in the anti-molecular orbital, so it's stable. And this is observed in the plasma at higher pressure. You know, when we say stable, this, of course, this molecule is not stable in the room temperature, but you can find out this kind of molecule can exist in some kind of condition, plasma and high pressure. I don't know whether you understand plasma or not, but we don't have time to talk about plasma, but plasma is a very interesting topic. So you have 1.5 bond, so you can see this in some kind of reactor. Okay, so let's go back to this one, this S2S and S2S. Is this stable? So it's 0. The bond order is 0, right? So barium molecule is not more stable than 2 separated barium atoms compared to this. That's what we learned. However, the barium molecule does exist in some kind of strict condition because the bond is very weak. Energy of bond is very weak. But barium metal is more stable. If you have 1 more of the barium atoms get together, is stable. This is what we call metallic bond. Okay, so now when we just finished the topic of S and S. How about S and P? So that means lithium molecular, barium molecular is S2S, right? So how about S and P? So how about lithium and fluorine? How about sodium and chlorine? This is what we call S and P mixing. And we want to know the orbital, the shape of the orbital or the structure, how it looks like. And also we want to know the energy. And we want to find out the molecular orbitals and energy level diagrams. Let's make example of the hydrofluoride. So hydrofluoride, the energy level diagram is S and P, right? So fluorine is 1s2, 2s2, and 2p5. So there are 7 electrons. Okay, again, let's write down the energy level diagram from low to high. So this is the hydrogen orbital, which is 1s. And this is fluorine atoms. There are 7 electrons. And you know, fluorine has 7 protons. So the fluorine will pull the electron closer to the nucleus. So of course, you know the energy will be lower than this hydrogen. Hydrogen is about 13.6 electron volt, right? Right, okay, so once you have these two atoms, you want to make it become molecular. So according to 2 rules, the first rule is conservation of energy level, energy states, conservation of energy state. Second is you have to follow alpha principle. So it looks like this. It looks like this. Again, this is the inner shell, so you don't need to worry about this. So you just look at energy will be the same. And these two, the electron is full with these 2 energy states. So these 2 will be here, will be in the same energy level. And when you think of this 1 electron and 1 electron, this is bonding, right? This is bonding. So according to the energy level, conservation of energy level, conservation of energy level, energy state, and alpha principle, you realize this energy state, one energy state, bounding molecular orbital has to be lower than these two, right? And anti-bounding molecular orbital, means it doesn't like to become molecular, right? So this level need to be higher than these two. So this is how it looks like. So this is bounding molecular orbital. This is anti-bounding molecular orbital. And of course, you only have 2 electrons. So you put these 2 electrons into this place. So as a result, if I ask you the energy of the hydrofluoride is higher than the hydrogen atom and the fluorine atom, or lower, right? Because hydrogen fluoride is more stable than hydrogen atom and fluorine atom. Okay? And then we understand there are 3, right? There are 3 energy states in 2p orbital. So one is 2px, one is 2py, one is 2pz. So this is 2pz, there are 2px, 2py. Okay? So how about the bond order? The bond order is, you have 2 minus 0. 1 is bounding molecular orbital, right? This is anti-bounding molecular orbital. So you have 2 minus 0. And you have equal and divided by 2. That will be 1. So this is what? Single bond. Okay? How about just in the previous slide, we talked about lithium fluoride. Am I right? Hydrofluoride. How about hydrochloride? Hydrochloride. That will be the same, right? But of course, the energy level for the chlorine will be much lower than the fluorine, right? Because you have more photon in the center. As you know that this energy is much lower than the fluorine energy level diagram, energy level. And this tells you the same story. You have bounding molecular orbital, anti-bounding molecular orbital. Instead, 2px, 2py, you write down 3px, 3py. Are you with me so far? Easy, right? No problem. Right, so when we talk about the single bond, homonuclear means you have 2 identical atoms. That means hydrogen, hydrogen, fluorine, fluorine, chlorine, chlorine. This is the homonuclear molecule. And another one is heteronuclear molecules. That means you have hydrofluoride, hydrochloride, something like this. Sodium chloride, something like this. So this is homonuclear molecular orbital. The energy level diagram looks like this, and heteronuclear molecules, the energy level diagram looks like this. Okay, so now let's take a look of another example of the single bond. Just now we talked about single bond. How about the single bond of the methane? We know the methane is sp3 hybridized, right? The orbital is hybridized because, as you know, from S to S and P, this is sp3 hybridization. So for the carbon, this is energy level is S2 here, and 3 energy states in the 2p orbital. And then once you want to make it become sp3 hybridized, you have to follow again conservation of energy state and alpha principle for the electrons. So you have 4 energy states. So once you want to make S2p sp orbital, how are you going to do that? You do the hybridization, right? And I have 4 energy states, so I need to draw the 4 energy states in the same energy level. So where are we going? Can I ask you, where are you going to draw? Is it here? 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, 3, 4? Where? Where are you going to draw the energy level, energy states? In what energy level? Here, right? You have to make the energy level between this one and this one. It should be 1, 2, 3, 4 here. So these 4 hybridized orbitals need to have a chemical bonds with hydrogen. Right? This is the orbitals in the carbon in atoms in the methane molecule. And we understand the energy level will be 2p larger than energy of the sp3 larger than the energy of 2s. Okay, so this is just give you an example. Right, so now when we talk about SS and SP, now let's think of the PP, P mixing and P mixing in the molecular orbitals. And we want to know the molecular orbitals and the energy level diagram. Before I, let me continue. So this is example of the PP, nitrogen and nitrogen. The I think let's play Kahoot first, because this is a topic which is spend a lot of time, so I don't want to have a break in the middle. Right. So one more time, you are happy once you get the answer right, right? Good. Okay, so now let's see the P and the P orbitals. And the first example is nitrogen molecule, and of course is multiple bonds. Again, let's write down. Let's draw the box. Write down the box notation for the nitrogen. So we have nitrogen. You have 7 electrons, right? 1s, 2s, 2p. So according to alpha principle, you can give 7 electrons in this notation, box notation. Okay, it looks like this. So you have this is nitrogen atom, and you have another nitrogen atom, and you put it together. I'm sure you understand, because for the p orbital, according to Schrödinger equation, you understand this x-axis. It looks like a dumbbell, right? It's like dumbbell orbital, and in x-axis, in y-axis, in z-axis. So when you want to put these two together, ladies and gentlemen, I want you to change this px to py, pz to px. You change this symbol here, because pz will be in this direction. You don't need to know why now, but actually just simply make it like this. So again, when they are far away, they don't have interaction. The shape doesn't change. But once you put these two together, and the orbitals is going to have interaction with another orbitals for the adjacent atom, in the adjacent atom. So what's going on? Again, before we do this, we see the Lewis structure. Lewis structure tells us that you have 2 electrons here, right? So you have triple bond. For the Lewis structure, you have 3 electrons and 3 electrons shared to each other, and you have a triple bond here. So let's think of this in z direction. So orbital interaction is 2pz, 2px, and 2py. So 2pz, that means you have this one here, this one and this one. So these two get together. So this is called node for the atomic orbital. This is node. Node means that the points of the zero electron density. So you are very sure for the probability there's no electrons in the center, and this is called node. Node. Of course, nucleus is here, so of course you don't have electron in this region. Node. So you plus another one. This is one electron, one nitrogen atom. This is one nitrogen atom. You put these two together, and this is if this is a constructive interference. What happened? It will become bigger, right? It will become bigger. So as you can see, this is called bonding molecular orbital. Bonding molecular orbital, these two put together, you become bigger. And of course, this is node too, right? This is node. So this is bonding molecular orbital. And when you put these two together, it looks like this. This one looks like this. And we call it sigma bond. Sigma bond. You know, when you are in high school, you learn sigma bond and pi bond, right? Am I right? Do you learn that? You did, right? Okay, so sigma bond is a continuous. The definition of sigma bond is the continuous electron density between nuclei, no lobes. So this is nuclei, and then sigma bond is that the electron is continuous electron density here. So there's no nodes between. There's no node between nuclei. So this is called sigma bond. So now let's take a look of the py orbital. Py orbital is here. So you put py orbital together, and how it looks like? We call it smear laterally. Smear laterally. Put these two together. Smear laterally. And this is atomic bonding, atomic orbital, right? Atomic orbital, and this is lobe. This is called node. Node, we already learned this, right? And to become like this. And this is the plane. There's no molecule. There's no electron density here. And this is called pi bond. The pi bond means what? Pi bond means that side-to-side overlap on hybridized p orbital. And the two lobes, this is called lobes. Two lobes and the one nodal plane. Nodal plane is that this is the zero density for the electrons. Okay, this is lobe, two lobes. Okay, so the same case for this for x-axis, right? X-axis. So you can see the same. You can get the same result as the py orbitals. So this is how it looks like. So for the pz, this is axially smear. For the px and py, this is laterally smear. For the axial smear, that means it's sigma bond. For the laterally smear is pi bond. So you have two pi bonds, one sigma bond. Okay? Well, and then you might think, Professor, just now we are talking about bonding molecular orbitals. How about anti-bonding molecular orbital? This is bonding, right? Bonding, it looks like this. How about anti-bonding? Anti-bonding, it looks like this. It's plus minus, so it's called destructive interference. Destructive interference, it looks like this. Of course, this is all according to the calculation. You cannot measure this. So they smear axially and they smear laterally. So this is bonding molecular orbital, anti-bonding molecular orbital. I don't need you to remember all the shapes like this, but you need to know at least just follow the rules, the theory of LCLMO. Right. So let's make a definition of sigma bond. Sigma bond is a single bond, or is the basic bond, right? So when we have SS, just now we talked about the bonds formed by s orbital and s orbital. This is always sigma bond, single bond. Because what? Because between the nuclei, there is a continuous electron density. This is called sigma bond. That's the definition, right? Okay, for example, the example is hydrogen molecule. How about sp sigma bond? Always. If you have an s orbital and a p orbital, it form a bond. This is always a sigma bond. So this example is because what? Because they smear axially, right? So this S and PZ and become like this. So this is the nuclei. And between nuclei, again, this is a continuous electron density between these two nucleus. So this is called what? This is called sigma bond. For example, this is hydrofluoride. Hydrogen is s orbital. Fluorine is pz orbital. How about P and P? If we smear axially, that means that's sigma bond. But if it's smeared laterally, that's pi bond, right? So that's what we just learned. So again, there are two nucleus, and between nucleus there's a continuous electron density. Again, this is called sigma bond. Okay, and laterally this is pi bond. So again, the definition of continuous the definition of sigma bond is a continuous electron density between nuclei, right? This nucleus. Okay, so sigma bonds are the strongest type of the covalent chemical bond. Compared to pi bond, sigma bond is stronger than the pi bond. We all know this, right? Okay, so now we already know the energy. We already know the shapes of the molecular orbital. So now let's think of the energy level, energy diagrams. So we use example of the boron 2p and boron 2p here. So you have sigma bond and you have pi bond, right? So when you do the 2p and 2p together, it looks like this. We have three energy states. Of course, sigma, as we know, sigma bond is the strongest bonding, so the energy need to be the lowest. Right? So this is sigma bond. And pi bond is weak than sigma bond, so it should be here. And these two is the same, so you need to be in the same level. And this is anti-bonding molecular orbitals for the pi bond. This is sigma bond. And because there are three energy states, so you have 6 energy states together. 1, 2, 3, 4, 5, 6. Okay? And you want to draw the pictures like this. This is bonding molecular orbital. This is bonding molecular orbital. As we just know, right? This is lobe. This is node, lobe. And this is anti-bonding molecular orbital for the pi bond. This is anti-bonding molecular orbital for the sigma bond. Right. And this is fundamental, it looks like this. But you might say, well, Professor, something wrong, because when I learn something, it's not like this. This is called S&PZ interaction. As I just showed you that it looks like this. Ideally, it should look like this. It should look like this for a boron. However, there's a S and PZ interaction. So it changed the shape, the energy level changed. Energy level changed. It changed to become like this because the energy of the sigma 2p orbital is changed by PS mixing. So the energy of the pi 2p and the sigma 2p are reversed. For the p, right? For the p, this is energy level here, and then because of the interaction, it looks like this. For the boron, energy, this one will be trapped down, and this one will be pulled lower, and this one reversed. Pi and sigma reversed, look like this for the boron molecule. Well, this is all I can tell you. It involves many complicated things I don't exactly know, and I don't have time to tell you. But what I want to tell you is that this is the interaction of the S and P. So it makes the S lower and make this energy level diagram reversed for the boron. And as a result, as you can see, these two electrons located in the pi bond here, in the pi orbital here. So also the P and S mixing changes the energy of the sigma and the sigma molecular orbital and sigma bonding molecular orbital. So such that they are no longer equally spacing. It should be equally spacing generally, yes. But now it's not equally spacing because of this and this interaction. So no longer equally spacing related to energy of the free S orbital. Okay, so it looks like this. And ladies and gentlemen, I don't need you to remember this. I don't want you to remember this. I just want to let you know, and you just need to know the interaction between this. So the energy level diagram change, and this reversed. And not all of these interactions happen because it depends on how many electrons in this energy level. So as you can see, for the boron, pi and pi bond and sigma bond reverse, right? So pi bond and sigma reverse for the carbon, pi bond and sigma bond reverse for the nitrogen. However, because you have more electrons for the oxygen, so this one return back. Pi bond is in the bottom compared to the sigma bond. Sorry, sigma bond is in the bottom compared to the pi bond. The same case as a fluoride gas. Oxygen gas and fluoride gas, there's no reverse. So as you can see, this bond always reverse for the boron, carbon, and nitrogen only. Okay? Because of what? S and PZ interaction. Right, these are some explanation for you to read. Please read this when you after the lecture today. Right, so let's start to know that energy level diagram of the nitrogen. So it looks like this, right? So we have 7 electrons, and then energy level diagram reversed because of S and P interaction. So we have 7 electrons. Let's put it here. Okay, this is nitrogen. We have 3 electrons. So as a result, we make 6 electrons. So there's no electrons in the anti-bonding molecular orbital, right? Okay, and we understand this is the shapes of the orbital. for the s, share for the orbital for the s, and share for the orbital in the y, and this is anti-bonding molecular orbital, anti-bonding molecular orbital. That's what we just know. Okay, how about bond order? Can you tell me the bond order? So here you know there are 3 bonds. So bond order will be 3, right? So can you tell me how to do the calculation? You have 6 electrons in a bonding molecular orbital. You have 0 electrons in an anti-bonding molecular orbital. And then you 6 minus 6 minus 0 and divided by 2. That will be 3, right? So it's triple bond. And as you know, the bonding energy for the 3 bonds will be 946 kilojoule per mole, which is much higher than the single bond hydrogen, 435. Okay. How about the energy level of diagram of the oxygen? So as I just told you, for the boron, carbon, nitrogen, there's an interaction between the s and p orbitals. But because you have more numbers of the electrons in the oxygen and fluorine, so the fluorine gas and oxygen gas, the orbital will change back to 2p here, 2py, 2pz. Okay, because of nuclear charge, it pull back. Okay, so please remember this. So let's write down the energy level diagram for energy level diagram. So actually we have 8 electrons, right? So we have 8 electrons in the s and 2s, 1, 2, 3, 4, 5, 6. Right, let's start to put these electrons into this molecular orbital. 1, 2, 3, 4, 5, 6, 7, 8. We have 12 in total, right? 8, 9, 10, 11, and 12. So we have 6 electrons in the bonding molecular orbital. We have 2 electrons in the anti-bonding molecular orbital. So this is called unpaired electron. Ladies and gentlemen, this is very important for you to identify what kind of molecule has magnetic, what kind of molecules is not attracted, is not affected by a magnetic field. And because of unpaired electron, this is called paramagnetism. Paramagnetism. Before we introduce paramagnetism, let's think of how many bond, what's the bond order of this oxygen molecule. So we have 6 bonding electrons, and then we have 2 anti-bonding molecular bonding electrons. So as a result, the bond order will be 2, right? 6 minus 2 divided by 2, that will be double bonds. So as you know, the double bond, the bond energy is 498 kilojoule per mole, which is larger than the single bond. So you know that triple bond, the energy of triple bond normally is higher than the double bond, and is higher than the single bond. Okay. So for the energy level diagram of fluorine, as you can see, so let's just don't waste your time. Let's put the electrons here. So we have 6 bonding molecular orbital. We have 6 electrons in the bonding molecular orbital. We have 6 anti-bonding electrons. So the bond order will be 1. Okay, which is about 160 kilojoule per mole. Right, so here I want to tell you about a little bit story about the paramagnetism. The paramagnetism is always happen in at least 1 unpaired electron orbitals, which is an unpaired spin in the atom molecules or ions. If we have unpaired electrons in the orbital, then that means it's always this kind of molecule or atoms is always paramagnetism. So what does that mean, paramagnetism? That this is unpaired, right? This is unpaired electrons. The paramagnetism is that if you don't apply magnetic field to this object, at that time there is no, the domain is randomly distributed. The magnetic domain is randomly distributed. So you don't affect by the magnetic field. But when you apply the magnetic field to this object, and the domain will follow the same direction, depends on the magnetic field. And this kind of phenomena we call paramagnetism. Okay, this is paramagnetism. And if you want to find out what kind of material has this kind of magnetic property, you always try to find the materials has an unpaired electron. So the paramagnetism is always weakly attracted because compared to paramagnetism, ferromagnetism is like it always has a magnetic. It's a magnetic material actually. It's a magnetic material, and diamagnetism is that you don't like. There's no magnetism at all. Okay, so this example for paramagnetism is aluminum, magnesium, platinum, or oxygen in a gas or liquid. That's why we just introduced to you, right? This is unpaired electrons in the anti-molecular orbital. Right, so this is some of the information for you to know. I don't want to waste your time. Please read it by yourself. So here is a very interesting experiment. Is the experiment for the paramagnetism phenomena of the liquid oxygen. So how are you going to produce liquid oxygen? By liquid nitrogen, right? So you put the oxygen gas into a liquid nitrogen, it will become liquid oxygen, something like this. So when you pour the liquid oxygen into this gap between the south pole and north pole of a magnetic, and the liquid nitrogen oxygen will trap here, will stay here. Why? Because as I told you, this is the phenomenon of paramagnetism. Once the material was applied to a magnetic field, the domain of the magnetic domain will align, and you will stay here. You will stay here. Okay, so the oxygen molecules are magnetic dipoles, but at the normal temperature they are remain unaligned since they are interacting with their interaction is very weak. Here I just want to tell you, when you talk about temperature, you always think of the energy, because the temperature high, the energy is high. Temperature low, energy is low. So why you want to make it become liquid is because at a room temperature, the energy is high. So the energy will disturb the magnetism very much. So you cannot find the magnetism. Okay, especially paramagnetism is very weak. So you need to lower down to the very low temperature, which is the thermal energy doesn't disturb the energy of the magnetism force. So this paramagnetism is weaker than the ferromagnetism, which is the magnetism associated with the iron or materials like ions whose magnetic dipoles interact strongly and align together at room temperature to create a very strong magnetic field. This is called ferromagnetism. So here I just want to show you the video, the experiment of this, very interesting. Please, we don't have time, but please just give me just give me 2 more minutes. So what I want to show you here is that, please work for me for another 3 minutes. So as you can see, this is, if you have unpaired electrons, this is paramagnetism. So for boron molecule, it's paramagnetism. For carbon, no, it's dimagnesium because there is no a pair. Okay, for the nitrogen, no. For the oxygen, yes, you have a single, you have an unpaired. For fluorine, no, right? For the bond order, boron is 1, carbon 2, nitrogen 3, oxygen 2, fluorine 1. So as you know, for the energy, this is 1 is low, getting higher, and getting low, getting low. So triple bond is the energy is highest, right? For length, of course, length for this is shorter because triple bond is shorter and longer. Okay. Right. So I think that's it for today.